Hello, here's um, my process for making a beam vibration analysis. Um, I first started off here in the workbench and I went ahead and transferred over a modal analysis system. And in there, I changed the units for this to be associated with aluminum. So I went over and looked up the physical properties of aluminum and I put them in here. I then went into my geometry and made a cross-sectional uh, beam of 10 by 20 centimeters that was 1 meter long, which I will show you what that looks like. So what I did here, I know you can't see anything, but this is because I went ahead and made a line, and this line has a cross section applied to it, which extrudes out from this plane and makes a solid beam from this point. So yes, this line, if splits off into the number of elements for this beam, which leads us into this page, which is in the model page. I went here. Now from here, you click this and it takes you here where I've already ran the simulation, but this is where I did most of the analysis. And so for like the 5 element uh, beam, I just changed the number of divisions for this to be 5, and I generated that. And that makes, the 5 element beam. And I noticed that like running the simulation with 5 elements usually causes weird looking things or not as accurate results, but this is the damped case. So here is where I changed whether it was damped or undamped. And I started off with hitting no. So this is the natural frequency of an undamped cantilever beam made out of aluminum. And I just hit solve. And I got the maximum displacements and each mode. So this was up and down, side to side mode, uh, bending mode, twisting mode, um, side to side bending, compression mode, I guess, and whatever this is. And I don't know what this one is either, but anyways, there's just multiple modes that are generated, but these are the ones that are the most important. The up and down mode and the side to side mode. And these generated these frequencies. Um, yeah, and that's pretty much it. And then for the damped cases, I went in here and I changed this to damped, and then I kept this at direct input and gave it a structural damping coefficient of 0.05 as as um so the beam would have 5% damping and kept everything the same. And then when I did that, I got the damped results for this cantilever beam, which when I did it for 5 elements, it looked a little weird for some of them, but for the ones that were important, it does look fine, and it was work. And as you can see, the amplitude is different as the undamped case, which is good. So yeah, that's how I analyze this beam, which, as you notice, the amplitude of deflection is much higher for this mode of deflection because of the nature of the cross section, it being much wider, allowing it to bend up and down much more this way than it can this way because it's much thicker. As if it was like flipped this way, then it'd be much thicker, and that's why for this deflection it is much less as per seeing as you can see here. So yeah, that is my analysis for this report.